Unraveling the Hubble tension, a deeper look into the expanding universe.
The vast cosmos has always been a source of fascination and mystery for humanity, and the pursuit of understanding its intricate workings continues to drive scientific inquiry. One of the most profound questions in cosmology is related to the rate at which the universe is expanding, a fundamental parameter known as the Hubble constant. Recent observations made by the groundbreaking James Webb Space Telescope, JWST, have thrown a fascinating twist into this cosmic puzzle, deepening the enigmatic Hubble tension. This brings into mind questions such as, is our present knowledge and understanding about our expanding universe and the cosmos completely wrong? Why should there be such a difference between the standard model of cosmology and the present findings? Should completely new physics be formulated, framed or constructed to explain the cosmos? In this video we shall take an in-depth look at the reported intriguing findings, the technical aspects, the implications they hold for our understanding of the universe, and the potential for new physics to resolve this cosmic conundrum. Hi friend! Welcome back to SciTech Buzz 1 channel. We wish to sincerely thank all the new subscribers of this channel. We have observed that 92% of our viewers haven't subscribed to our channel. If you haven't as yet subscribed, kindly consider doing so after watching this video, since it would encourage us to do more. Now let us delve into the analysis of the subject matter. The Hubble tension. At the heart of this cosmic mystery lies a discrepancy in the calculated value of the Hubble constant, which describes how rapidly the universe is expanding. According to the Planck satellite's observations, the Hubble constant should be around 67.4 km per second per megaparsec. A megaparsec is a unit equivalent to about 3 million light-years. However, measurements obtained by the Hubble Space Telescope, based on observations of distant stars, suggest a significantly higher value of 73 km per second per megaparsec. This profound disagreement between these two seemingly reliable methods is commonly referred to as the Hubble tension.
The James Webb Space Telescope's contribution.
In the quest to resolve the Hubble tension and gain a clearer understanding of the universe's expansion, the James Webb Space Telescope has emerged as a revolutionary tool. The JWST is equipped to observe a unique set of cosmic beacons, Cepheid variable stars. These stars exhibit periodic fluctuations in their brightness, allowing astronomers to gauge the amount of light they emit. By comparing a Cepheid star's observed brightness in telescope images with its expected brightness, based on the frequency of its brightness variations, scientists can accurately measure the distance to these stars. Furthermore, shifts in the color of light emitted by Cepheid stars provide crucial information about their movement, how quickly they are moving away from us. By combining these distance and speed measurements of Cepheid stars, astronomers can determine the rate of expansion of the universe. The JWST's edge in this cosmic pursuit lies in its superior resolution, allowing it to pierce through the dense stellar population surrounding Cepheid variable stars. This advancement enables the telescope to obtain data with considerably reduced uncertainties and minimal confusion arising from nearby stars compared to the Hubble Space Telescope. The JWST validates the Hubble Space Telescope's measurements. The details reveal that the James Webb Space Telescope's observations corroborate the measurements made by the Hubble Space Telescope. Astonishingly, this validation indicates that the Hubble tension persists even with the enhanced data quality provided by the JWST. This outcome reinforces the perplexing nature of the discrepancy and raises the stakes in the ongoing quest to unravel the universe's expansion rate. Skepticism and challenges. Despite these intriguing findings, not all astronomers are ready to wholeheartedly embrace them. Wendy Friedman, an astronomer from the University of Chicago, offers a word of caution. She notes that the JWST's observations are currently limited to galaxies that are relatively close to us on cosmic scales. In such proximate regions, it is relatively easier to distinguish Cepheid variable stars from the surrounding stellar populations. However, as one moves to more distant galaxies, the task becomes increasingly challenging due to the decreasing resolution of the telescope. Therefore, the true test of the Hubble tension lies in its ability to withstand scrutiny in more remote cosmic realms. A glimpse into the future. The new observations hinted a tantalizing glimpse into the future of Hubble tension research. Preliminary data from the James Webb Space Telescope, presented during a conference in Baltimore dedicated to the first year of JWST science, includes observations of galaxies located up to 140 million light-years away. These galaxies represent some of the most distant celestial objects ever studied using Cepheid variable stars. Astonishingly, these initial results align with the measurements obtained by the Hubble Space Telescope. While these findings await the rigorous process of peer review, they offer a ray of hope for those convinced that the Hubble tension is indeed a significant cosmic puzzle. Implications for cosmology. George Efstathiou, an astrophysicist from the University of Cambridge, expresses his astonishment at these intriguing developments. Efstathiou, a member of the Planck satellite collaboration, had previously contributed to a lower estimate of the Hubble constant based on observations of the cosmic microwave background, the oldest light in the universe. This lower estimate, in conjunction with the Standard Model of Cosmology, suggested a Hubble constant value that differs from the measurements obtained by the JWST by about 5.6 km per second per megaparsec. As it currently stands, there appears to be no fault found in either the Planck satellite's measurement of the Hubble constant or in the JWST's observations. Instead, the Hubble tension points to a potential issue with the Standard Model of Cosmology itself. The Standard Model, a foundational framework in cosmology, has withstood numerous challenges and tests over the years without showing signs of breaking down. It was constructed in response to the discovery of the accelerating expansion of the universe, an achievement that earned cosmologist Adam Rees and his colleagues a Nobel Prize in Physics. This model incorporates complex concepts like dark matter, dark energy, and other fundamental factors to provide a concise explanation of the universe's behavior. However, the Hubble tension suggests that there may be facets of the universe that remain unexplained within the confines of the Standard Model of Cosmology. This enigmatic disagreement challenges the very foundations of our current understanding of the cosmos. New physics on the horizon. Cosmologist Adam Rees of Johns Hopkins University acknowledges that resolving the Hubble tension may necessitate the introduction of entirely new physics. Over the past decade, researchers have proposed a variety of hypotheses to explain this cosmic puzzle. These range from the existence of exotic dark matter and dark energy to the presence of novel particles and even magnetic fields in the early universe. However, none of these hypotheses have provided a definitive solution to the Hubble tension. In essence, the universe appears to be telling us that there are phenomena and forces at play that extend beyond the boundaries of our current understanding. The mystery of the Hubble tension serves as a reminder of the ever-expanding frontiers of scientific exploration. Conclusion. In conclusion, the details discussed in this video takes us on a journey through the intricate realms of cosmology, highlighting the captivating enigma of the Hubble tension. This cosmic puzzle centers on the disagreement in measurements of the universe's expansion rate obtained by different methods. The James Webb Space Telescope, with its superior capabilities, has added a new dimension to this quest by corroborating the Hubble Space Telescope's measurements, reinforcing the enigmatic nature of this cosmic conundrum. Nonetheless, skepticism remains, particularly with regard to the tension's persistence in more distant galaxies. The true test of the Hubble tension's validity lies in its ability to withstand scrutiny across the vast cosmic expanse. These challenges notwithstanding, the ongoing pursuit of understanding the universe's expansion holds immense promise. The implications of the Hubble tension extend deep into the foundations of cosmology. While the Standard Model of Cosmology has been a stalwart framework, the tension hints at gaps in our understanding. It challenges the very core of our cosmic knowledge, beckoning the possibility of entirely new physics to resolve the enigma. In the grand scheme of cosmic exploration, the Hubble tension is not a cause for despair but rather an exciting opportunity. It presents the prospect of advancing our understanding of the universe, whether by confirming the current model or by unveiling the mysteries that lie beyond. As we venture deeper into the cosmos, the universe continues to reveal its secrets, inviting humanity to journey further into the unknown. My friend, if you have found any value in this video, then kindly click on like button as an encouragement to create better quality content. Please share this video amongst your family members, friends and in your social media networks so that this information might benefit others. Don't forget to subscribe to SciTech Buzz 1 channel so that you will not miss out on any of our forthcoming videos. Thank you.